Hi, GS142 students. I'm here to help you go through the Plate Tectonics Lab 2. Now, there really isn't as much of an informational document for this lab. I'm expecting you to fully read and the sections in the textbook about this material, and then also to look at my lecture notes material that I supplied you for Plate Tectonics. So in the lab folder, there's three different items. One of them, here, let me share screen, is the actual question worksheet that you're going to be submitting in your answers for into Moodle. So I say here, you should have done the readings in chapter 2 and 9 and watched and listened to the PowerPoint lecture on Plate Tectonics before doing this lab. You will need to access these other two files. There's a PDF National Geo Ocean Floor Map file, and that is, let me go in here and show you that. Okay, this is the National Geo Ocean Floor Map file. And back to this. And there's a document, a PDF file of supplemental maps that has two plate boundaries maps, an up-close map of the tectonic configuration here in the Pacific Northwest, an up-close map of the tectonic configuration of the Caribbean, and an epicenter of earthquakes map of the Arctic Ocean, which is oriented upside down compared to the National Geo Ocean Floor map of the Arctic that was in that document that I just showed you. Okay, so let me go out and show you that real quick. Here, so here's one of the plate boundary maps. Here's second plate boundary map. There's the one of the West Coast here in North America. There's the Caribbean, which is a lot more confusing and detailed than it shows on most ocean floor maps. And then here is the Arctic, and you can see the Greenland and Canada over here and Asia on the lower part of that map. Okay, so let's go back here. Now, you can print these map pages if you wish. They would be easier to read, more convenient if actually you had a printed copy in front of you, but of course that's going to be a certain size. You're not going to be able to blow them up, so totally up to you. If you don't have that ability, hopefully you do have a screen that's large enough so that you can plus and minus, and with the magnifying glass icon or however your document is reader is going to do it. So you gather the answers for the questions below about the indicated areas on the 4 different ocean floor maps, one of which is duplicated. I have an Atlantic Ocean A and B, the Indian Ocean, the Pacific Ocean, and then the Arctic Ocean, which is all on that one document. Some questions ask you to refer to the supplemental maps in the other second informational PDF on Moodle. Submit your answers on the site for submission of these answers starting on Thursday, April 14th at 6 p.m. and ending on Wednesday, April 20th at 6 p.m. And you get 3 attempts to put them all in, correctly. Each attempt is going to build on the last, so it'll only re-ask you questions that you got wrong or incorrect the first and second time around. Okay, so I'm going to be going back and forth here, so this is going to be interesting. First, we're going to look at Antarctic Ocean Map A. And I'm wondering if this thing's going to let me print. Maybe I'll print myself a copy of this so I don't have to go back and forth. We're having a hard time getting the tech guys to put us all back together, so I can't print. Anyway, I'll just go back and forth. Okay, so first we're going to look at the red arrow on the Atlantic Ocean Map A. This arrow is pointed at Iceland, a large island which has ongoing volcanic activity, some of which is due to the fact that Iceland is the location of a hotspot, If you were to visit Iceland, you would be able to visit a place where you can stand with one foot on one lithospheric plate and the other foot on another lithospheric plate, because it's also positioned on top of a mid-ocean ridge. And this is where new magma is coming up, making new rock, and then it's splitting apart, going away from each other. So it's like two halves moving away from each other. So what kind of boundary is that? Is that convergent, divergent, or transform? So let's go take a look at that map. Oops, wrong one. We gotta get over here. And then let me rotate this. Okay, so here's Iceland, right? Here's the mid-ocean ridge right here. And Iceland is also a location of a hotspot. So it's got lots of volcanic activity, and it's built up tall enough that it actually is a pretty good sized piece of land out there. Okay. So is that coming together, which is convergent? Is that splitting apart, which is divergent? Or is that sliding past each other, which is transform? Okay. Back to the questions. The two plates involved are, choose the two that are involved there at Iceland. So you think about what's to each side of that part of the Atlantic. Okay. And then I've just pretty much been telling you, besides the mantle plume below, which is the cause of some of the ongoing volcanic activity, Iceland has grown to the size it is because it also has what? Okay. If it's the type of boundary, if you pick the type of boundary correctly here, then you're going to be able to pick the volcanic activity that's taking place there. And I already mentioned it, I believe. I have a tendency to do that. Sometimes I forget what I'm asking in the future and I tell you the answer. Now we're going to move to the yellow arrow on the Atlantic A map. This arrow is pointing to a long dark line, and specifically at a small segment of the mid-ocean ridge where the rock to the north of the dark line in this segment is moving east, and the rock to the south of the dark line in this segment is moving west. That small segment of the long dark line is what type of plate boundary? Okay, so let's go over there and look. That's this line right here. Let me go in here and blow it up. Okay, so here's the mid-ocean ridge where the rock is being formed and is pulling apart. So this area is moving that direction, and this area is moving that direction. So that is what kind of boundary? Is it convergent, divergent, or transform? You have side-to-side motion. The correct choice of boundary for question 4 could also be considered what type of fault? Okay, that type of fault is actually what the San Andreas fault is too. San Andreas down in California is that same type of fault. Okay. Now moving on to the green arrow, and it says access the supplemental map of the Caribbean to help with these questions, these two. This deep area in the Caribbean is arcuate in shape. What specific type of plate boundary is this? Add an extra letter in there. Okay, so let's see, go away from this. Back to here and then to the supplemental. Okay, so here is the area we're talking about. Area we're talking about. Let's see where the arrow was first. Right here. Okay, come over here. What are they calling that right there? What kind of boundary? And the same thing here. What kind of boundary? And then here is the up close. Okay, so it's this right here. So what was our questions then saying? What kind of crust is to each side and what's going on? It's definitely a subduction zone. Okay. So is there a continent on one side and the ocean on the other? Are they both oceanic? And then which one of these is true? This type of plate boundary would have an associated volcanic arc. What's the name of the type of volcanic arc that is building at this plate boundary? Meaning that, is it a continental arc or is it oceanic arc? Okay. That's just, you have to choose which one. Blue arrow in the Atlantic A map. The blue arrow is pointing at a dark line, which is a crack in the oceanic crust where the rocks to both the north and the south of this crack are moving to the west. This is not an active plate boundary. The two sides are moving with each other. So this feature would be called a blank zone. So let's go out and take a look at the map. Blue arrow right here. Well, I'm sure it mentions this in the lecture notes and especially in the textbook, I'm sure it does. But where we had movement taking place between these two, notice that there's a line coming out this direction too, where both of these are moving this direction and both of these are moving that direction. That's what's going here, right? Is that both this rock and the rock that the blue arrow is on are both moving to the west. So there's a word that you use for that. I mean, it's a break in the rock, right? It's a crack in the rock, but there's no movement along it. So it's not what we would call a fault anymore, because faults have movement of some kind along them that is opposing motion, shall we say. But since both of these parts of the rock are moving at the same, they're moving, but they're moving together in the same direction. So what's another word for a crack? When you think of like glass, and if you crack glass, what's that word? And it most definitely is mentioned in the textbook, and I believe also in my notes. Okay. So moving on then to Atlantic Ocean B. And I don't remember what star I got first. So let's go back out here and take a look at the question sheet again. Yellow star. This is the area where a magnetometer was towed back and forth across the mid-ocean ridge back in the 70s or something. The red readings that were collected from this area and other places around the world at similar plate boundaries were a major argument to substantiate Harry Hess's theory of seafloor spreading. These readings showed that, all right, what did they find out about that area by towing a magnetometer? Okay, is it that the age of the crust to each side of the mid-ocean ridge gets older and older the further you go to each side of the ridge? Is it that the thickness of the sediment increased as the readings were taken farther and farther to each side of the ridge? Or was it that the magnetic anomalies of the ocean crust to each side of the mid-ocean ridge are close to mirror images of each other in width? In other words, the anomalies are symmetrical stripes of reverse and normal polarity to each side of the ridge. I would think that one would be obvious. Hope. Now, moving on to the blue stars and the red stars. We know that all the continents about 250 million years ago were joined together into a megacontinent that was named Pangaea by Alfred Wegener over a century ago. Just gonna let it there. When continents rift apart and new ocean basins are being made, the edges of the continents, or the continental shelves, will get wider and wider over time due to the addition of sediment onto the edges of the continents from rivers flowing out into the ocean. Look at the width of the continental shelves in the North Atlantic, which is where the blue stars are, and the South Atlantic, which is where the red stars are. North America, Eurasia, Africa, and South America moved independently for some time. I mean, they weren't connected to each other like they are now for some time after the breakup of Pangaea. Which continental rift occurred first? Was it in the North Atlantic between North America and Eurasia? Or was it in the South Atlantic between South America and Africa? Okay, so let's go out and look at that map. So here's the two blue arrows sitting on top of the continental shelves in the North Atlantic. And here is the two red arrows, stars. And you can see the edge of the continent, this shallow area on the edge of the continent here. And which one is wider? Plus, which ocean is wider? Because the wider the ocean, the longer it's been opening up. Okay, so hopefully you can answer that one pretty easily. And I think we have one last thing on here. That's this green star here. Okay, so what are we asking about the green star? This is a line of volcanoes which do not occur along a plate boundary. What is the most likely explanation for the placement of these volcanoes? They were formed above a now dormant subduction zone. They were formed at a now dormant mid-ocean rift. They were formed by a mantle plume at a hotspot, or they were formed by a now dormant transform boundary. Well, this last one, is there volcanism on a transform boundary? So it has to be one of the other ones, probably. So we're either going from a now dormant situation to, it was active in the past and now it's not, to something that was, maybe still active, though maybe not in the same position. Okay, so let's go back and look at that map again. Okay, here's the mid-ocean ridge, and there's passive margins along here. There's no subduction zone along the edge of either, of these continents. So what could account for this line of volcanoes going off sideways like that on the bottom of the ocean floor? Now, whether any of these, they're calling them seamounts, whether any of them are even tall enough to be islands, I don't think so. Okay. So I'll let you think about that one, answer that one. Now we're going to go on to the Indian Ocean. We're going to look at the brown star first. This star shows the approximate position of Mount Kilimanjaro, the tallest volcano on the African continent. This volcano developed this position because, is it directly over a mantle plume hotspot? Is it one of the north-south line of volcanoes that are forming on the overriding plate above a subduction zone? Or is it one of the volcanoes with the general north-south trend, which are positioned along the normal faulting of a continental rift? Okay, so let's go out and look at the map. Here's the Indian Ocean, so let me rotate it. Here we go. So here's the brown star. Now, if you've looked at the lecture notes and you've read the book, then you know what is going on in this part of Africa. Okay, and notice where these lakes are. Those lakes are filling in, and what does it say here? Great Rift Valley. And these lakes are filling in these low areas in this rift. So right there, and when you break rock like that, where it's stretching apart, that part of Africa is stretching, and the rock breaks, and those breaks in the rock are deep enough that it allows magma to move up along those breaks, along that normal faulting. And you get volcanoes like Mount Kilimanjaro, Mount Kenya, and a bunch of others. Okay, so I think you get that answer pretty easily. Yellow star, choose any and all answers which are true for this locality. It's a possession of a triple junction. Triple junctions are specifically mentioned in my lecture notes, and I can't see that Marshak wouldn't have mentioned them in the chapters either. That's that three-pronged break that happens when rifting of a continent is first getting going. Okay. And those rifts develop into ocean basins. This is the locality of position of active volcanism. Well, let's take a look at what that is that spot is doing. This locality will perhaps at some future time be covered in ocean water. This locality will most definitely at some future time be covered in ocean water. Well, it can't be both of these. So we're gonna have to decide which of these, if either one. Let's go and take a look at where that yellow star is. Here's the yellow star. Here's the Red Sea. Look at it, it says it's a rift valley. It's also covered in ocean water. Here's the Gulf of Aden. The Gulf of Aden has got actual oceanic basalt on the floor there. It's actual ocean floor. Okay, so here we got two arms, and then this is the third arm. So it's definitely a triple junction. If indeed you are ripping the ground apart, then it's probably a good chance that there's magma coming up from below. And in fact, there's little volcanoes on the bottom and in this area all over the place. And there's one of them, it's a very, very desolate part of the Somali Peninsula here, but it is a lava lake that's been in existence for hundreds of years. You know, it's just got a constant, kind of like there's a lava lake in one of the craters on Kilauea too, in Hawaii, where it takes a long time to walk out there, and then there's this big, huge hole in the ground that's got all of this boiling lava in it. So yes, it's a place of volcanism. Now, if you remember a triple junction, though, that the three arms of a triple junction, they can all open. In fact, the Indian Ocean has got an example of that in another spot that we're going to talk about in a little bit. But they don't always open. Because remember, even here in North America, we have like a failed rift that it was a part of a triple junction arm that never opened, that the Mississippi River actually took advantage of that weak spot. And that's, so that rift, that ancient rift has been buried in sediment, younger sediment there going up through the Mississippi Valley. So they don't have to open. They can, but they don't have to. So there's no guarantee that this is going to continue to open and become a new ocean. Okay. Certainly a lot further along in the future than any of us are going to be around to see. Okay. All righty then. Number 14, the dark green star. This mountain range is still building. What is the specific type of plate boundary at this locality? So now you're going to have to choose, what kind of plates, either oceanic or continental or what. Is there still active subduction going on or not? And then is it pulling apart or is it coming together? Okay, so let's go take a look at the map. They're up here. So here is the subcontinent of India, and it's pushing up into Asia and building the Himalaya. Okay. So this is a continent and that's a continent. So then the question for you, and they're coming together. So now the question for you is there any subduction going on? Because subduction is when a plate actually goes down and gets dragged down into the interior. So at this point in time, no, there's no subduction. Now, when India was further south and the leading edge of the Indian plate was oceanic crust, because it was, then yes, there was subduction. But once the continental rock itself came into proximity and started pushing up into Asia, no more subduction. Okay. Light green star. This ridge is called the 90 East Ridge because it is almost coincident with 90 degrees east longitude. With the breakup of Pangaea, India and Australia moved to the north-northeast away from Africa and Antarctica. And both of them, India and Australia, are positioned on what we call the India-Australian plate. The rocks of this ridge have been dated at about 81.8 million years old at the northern end and an age of 43.2 million years on the southern end of the ridge. So they're not all formed at the same time, right? The northern end is a lot older than the stuff at the southern end. They get progressively younger as you go south. The direction of plate movement and this age information points towards this ridge having possibly been formed of volcanoes that, was it a now dormant oceanic subduction zone? Were the volcanoes that formed along an active spreading mid-ocean ridge? Were they volcanoes that formed above a stationary mantle plume or a hot spot that might not now be working? Okay, so let's go back and take a look at that. Okay, so here's the East Miami Ridge. It's really linear, right? So the volcanoes up here, almost 90 million years old. And the volcanoes down here, 40-something million years old. Okay, there's no trench here. So it can't be a subduction zone. This is where the new ocean crust is being made. And this plate's moving that direction. So what do you think? And now the red star, this locality is what? Center of the triple junction, has been moving north since the breakup of Pangea, was the center point for continental rifting in the initial stages of the breakup of Pangea, is an area that would experience earthquakes due to movement along thrust faults. Thrust faults are when rock is being pushed together. Is an area that would experience earthquakes due to movement along strike slip faults. Strike slip faults are where rock is sliding past each other. No up or down movement. Okay. So let's go out and see that area. This is basically the mid-ocean ridge, right? Look, it's got 3 prongs. So do you think it used to be a triple junction? Yes. Well, if it's a mid-ocean ridge, it's going to have side-to-side motion, right? There's going to be offset, they're not, like right here, there's offset. So you don't see the big, huge, really, really long cracks like you do in the Atlantic, but they're still there. Indian Ocean is weird on the bottom, it really is. Okay, so what else? India and Australia and Africa actually is a lot further north too. So India and Australia used to be back down here towards Antarctica with Africa. So, think about where it broke apart. When it broke apart, they were clear down here. So the whole thing is moved, right? New ocean crust is being made around Antarctica. That's pushing the mid-ocean ridge itself to the north and the east. Okay, as this plate moves, the new crust is being made. It's pushing all this stuff to the east, and new crust being made over here is pushing the ridge itself to the north and east. Okay. What were the other things that were on that list? So yes, it's the center of a triple junction, has been moving north since the breakup of Pangea. Yep. It was the center point for continental rifting. Yep. It was the middle of a triple junction. Would it experience earthquakes due to thrust faults? Nope. There's no convergence, right? There's only divergence and side-to-side motion along a mid-ocean ridge. Now the blue star. This locality has what specific type of plate boundary? So you're going to have to figure out which kind of plates to each side are the oceanic, with one continental and the other oceanic. They're all subduction. And then what kind of a boundary do you have subduction take place at? Okay, so blue star, right? Here's the island of Sumatra. This is Java. This is a trench. And in fact, the 2004 tsunami that took place in the Indian Ocean was generated by movement along this plate boundary. And the movement started somewhere right in here. You know, the rock broke and then it went pop, 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 pop for almost 700, something like 700, 650, 700 kilometers. And that's why the tsunami was so huge, was because there was a huge amount of movement of rock on the ocean floor. And it's about the same length as the subduction zone that we have here in the Pacific Northwest. So if we had a really big earthquake, you know, a 9 point whatever earthquake, like they say we're going to have eventually, it's going to generate a really big tsunami. If it breaks, especially if it breaks the way it did here. Okay, and then you get a little tsunami, or a tsunami that comes up on, you know, the nearby land. And then the tsunami went around to the side here and just nailed Thailand here. Came out here, took 2 hours to get to Sri Lanka, and then wrapped itself around Sri Lanka and devastated this part of the coastline of India and Sri Lanka. And then 8 hours later, the tsunami got to the coast of Africa, although it wasn't very big by that time. Not near as big as it was here. So what kind of boundary is that? Well, yes, there's land masses here, but really what the Sumatra and Java are is just a volcanic island arc system. Okay, it's like oceanic volcanoes. You know, the edge of the continent's way up here. Okay, so it's oceanic. Yes, there's a subduction zone. That's a trench. And is it going together or is it coming apart? Right? One of them's divergent, one of them's convergent. Which one is it? They're coming together, right? The plates are moving towards each other. So what is that? What do we call that type of boundary? All right, now we're going to move on to the Pacific Ocean. The red star that we're going to look at in the Pacific Ocean is what plate's it positioned on, what kind of plate is it positioned on, and what kind of a volcanic arc does it have? Is it a volcanic island arc or is it a continental volcanic arc? Okay, so let's go take a look at the red star in the Pacific. There it is right there. Here's Japan. Here is the Philippines. Here's the island of Borneo. There's Java and Sumatra again. Papua New Guinea. Okay. There is the Marianas Trench, the lowest spot in the entire Earth's ocean is the Marianas Trench. It's like over 30,000 feet deep. It's deeper than Everest is high in elevation. Really deep. Okay. And then there's another trench here, the Philippine Trench. So in this place, the Pacific Plate is going underneath this plate. All right. And here's the edge of the continent way over here. Okay. So what are we saying about this? Is that red star positioned on the Pacific Plate or is it positioned on the Philippine Plate? I just pointed out to you what was the Pacific and it's going underneath that plate. So it's not on the Pacific. Is it positioned on an Oregon crustal plate? I mean, or oceanic, excuse me, not continental, right? It's oceanic, not Oregon. Is it positioned on a locality which includes a volcanic island arc? Well, if you've got the Pacific Plate subducting underneath the Philippine Plate, then there has to be volcanoes building on the top of the Philippine Plate. If you've got subduction, you're going to have volcanoes. But there's no continent around, right? So the volcanoes are going to form an island arc system. And then some of them are going to be seamounts. You know, they're not going to be tall enough to be islands, but there's no continent, so it can't be a continental volcanic arc. Now we're going to go to where the gold star is positioned. This star is positioned, choose any and all that apply. It's positioned on the overriding plate in an oceanic subduction zone. We'll see. It's on a convergent plate boundary. Well, if A is true, then B is going to be true. But if A isn't true, is it on a transform boundary? And then again, is it positioned in the area of a volcanic island arc? Well, if you've got A and B true, then you probably have D being true too. So let's go out and take a look at that area. That is the gold star. Gold star. Here, up here in the north. Well, the edge of the continent is, I know it's this is a continental shelf here. Okay. But this part is oceanic. Okay, it's not the actual continental shelf, is just sediment. Okay, that's covering this part. That's why it's so shallow. But this is the Pacific plate down here, and it's going underneath the North American plate. And in this particular spot, it's building the Aleutian Islands out here. And they go almost all the way over here to Kamchatka Peninsula. That's definitely the most westward spot of the states of North America anyway, the United States. So what do we got? Well, if we have a trench, then we have a subduction zone. This is oceanic, and this is also oceanic because it's, you know, a bunch of little islands out here. These volcanoes are not building on the edge of a continent like they are here in the Pacific Northwest. Okay, so it's everything but the transform. Go back to that question. Yes, it is on the overriding plate at the oceanic subduction zone. Yes, it is on a convergent plate boundary. And yes, it is in the area of a volcanic island arc. Now we're going to go to the light green star. This dark line is it an active divergent boundary? Is it an active transform boundary? Or is it an inactive fracture zone? And that was one of the questions I asked you about the Atlantic was, what do you call that place where both plates or the pieces are moving at the same time? So light green star here. Okay. So here's the mid-ocean ridge coming up like this. And then it goes up into the Sea of Cortez here, and that propagating up is what's splitting the Baja California off of Mexico. It's going to continue to propagate. And then the San Andreas Fault actually leaves off of Point Reyes here, north of San Francisco, and goes into this fault. See, but there's no active divergence anymore. All of this is just moving this direction north. Okay. And then there's the Wanda Fuca plate is just a little tiny one here. All right. So hopefully you can get the answer to that one okay. Dark green star. Use the supplemental map of the Pacific Northwest tectonic configuration to help you answer these questions. This star covers the position of the state of Oregon. Oregon sits on a convergent boundary which extends from Northern California up to southern British Columbia. Directly to the north and south of the convergence between the Wanda Fuca plate and the North American plate are what type of plate boundaries? Okay, so now this is not where the San Wanda Fuca plate is going underneath North America. Okay, we're talking about to the north and the south. Okay, so are they the same? Right? Are they divergent boundaries both to the north and the south? Or are they transform boundaries to the north and the south? Or do we have divergent to the north and convergent to the south, or convergent to the north and divergent to the south? So let's go out and take a look at that supplemental map. There we go. Rotate. Whoop. I want to rotate. And this one, well, it shows to the south that there's that's transform, right? True. That purple two arrows. But what about, let's on this map, north of the little tiny Juan de Fuca, they're showing it being purple, going up until you get up around Anchorage. Okay, going up past, and what do you got going on here? Same idea, you know, the gold color is a transform fault that they're showing as being up in that area, which means that both to the north and the south of the Juan de Fuca, it is transform boundaries. The southernmost volcanic mountain of the Cascades Continental Volcanic Arc is Crater Lake, which is in the southern part of Oregon, Mount Shasta, which is in the northern part of California, Mount McLaughlin, which is also really close to Crater Lake in Oregon, and then Lassen Peak, which is in California. So let's go take a look at that supplemental map again. So here's all the big volcanic mountains of the Cascades. And there's Mount McLaughlin. Mount Mazama is Crater Lake. Here's Mount Shasta, and then Lassen Peak is the southernmost volcano of our Cascade Range. Light blue stars. Choose any all statements below which apply are correct for this line of geos, seamounts, atolls, and islands. The bend in the line has been dated at approximately 50 million years ago. Okay, so do the volcano features formed at a location of a hotspot? This line of volcanoes formed on top of the Pacific Plate. Is that true? The orientation of the two parts of this line of volcanoes suggests that before 50 million years ago, the Pacific Plate was moving almost due north, whereas after that time, the Pacific Plate has been moving to the northwest. Or is it the orientation suggests that before 50 million years ago, the Pacific Plate was moving to the northwest, whereas after that time, the Pacific Plate has been moving due north. And then all of the volcanoes in this line will eventually subduct into the Aleutian Trench. So let's go out and take a look at what we're talking about. Talking about this line right here. So this is Hawaii. The most southeastern part of this chain is the Big Island of Hawaii. There is another one. There's a bump forming to the southeast of the Big Island of Hawaii, but it's still, it's not anywhere close to being an island yet. It has a long time to grow before it gets up there. The Pacific Plate is moving this direction. Okay, it's moving towards the northwest. So this is the youngest. It's around 50 million years of age here, and the stuff that's up here is somewhere around 70 something million years of age. So if it's like 0 age here and 50 here, and yet 70 something, almost 80 here, this segment of the arc, or the line of volcanoes, excuse me, was made between about 50 and 70 something million years ago. So about 50 million years ago, this spot right here was here. And this is out in the middle. I mean, this is the Pacific Plate over here too. So it's definitely out in the middle of the Pacific Plate. And how do you get a line of volcanoes coming up through the middle of a big plate like this? It has to be a hot spot. The hot spot is located right there, and the plate is moving over it. And so the plate is taking the volcanoes away from the hot spot and moving them into deeper water. Okay, So this segment moving to the northwest is between modern day and about 50 million. This segment is from 50 million to about 80 million years ago. Okay, so going almost due north is what happened before 50 billion years ago. Whereas since 50 million years ago, it's been going to the northwest. Now think about it. If the entire plate keeps on going this direction, are these volcanoes here ever going to go down the Aleutian Trench? No. By that time, all of these, the whole plate's moving to the northwest. So these volcanoes are going to start subducting down the Kuril Trench before too long. And then by the time this row gets there, they're going to be going down here into the Japanese Trench, most likely, if nothing else changes. So no, they're not going to go down the Aleutian Trench. Now the rest of the Pacific Plate will continue to do that, but not this line of volcanoes. Okay. In February 2011, the South Island of New Zealand experienced a 6.2 magnitude earthquake centered near the city of Christchurch. This earthquake occurred due to what type of plate boundary? Now that's the South Island of New Zealand, okay? So let's go out and look at that purple star. And then it asks us the plate boundary to the north of the North Island of New Zealand is what kind of plate boundary? Okay, so let's think about that when we're out there looking at this too. Here's the purple. So Christchurch, this is the South Island here. That's the North Island. Okay. Let's go to our plate map, our plate boundary maps, and take a look at that. This one might be the most instructive. Right, here's New Zealand. So there's a small subduction zone here to the south of the South Island, but really going up most of the South Island and through the North Island, it is a strike slip fault, the transform plate boundary. And it's only a 6.2, which is not that big of a earthquake. Most subduction zone earthquakes are like 7s and 8s and 9s. Whereas the transform boundary, there are 6s and 7s and high 7s, but rarely getting up above 8. Okay, so the first answer would be transform boundary, I believe. Okay, now what about to the north? Well, to the north of the North Island, it's a convergent plate boundary. Okay, and specifically, if you see the teeth like that, the teeth are pointing into the overriding plate. So what that means is that the Pacific Plate is going underneath the edge of the Indo-Australian Plate in this area. Okay, so let's go back and see which answer that is on our question sheet. All right, so this earthquake occurred due to what type of plate boundary? Well, it's not convergence, not divergence, transform, right? Two sliding past each other. And then to the north of the North Island of New Zealand it's definitely a convergent subduction zone with the overriding plate on which side of the boundary, right? The teeth point into the plate. So you can go back to that picture if you don't know it. You can go back to that picture, and the direction that the points of the teeth are pointing to is where is the top plate, is the overriding plate, and the subducting plate is on the other side of that line. Okay. Now we're going to look at the brown star in the Pacific. This star is located on what type of specific plate boundary? Okay, what's the two plates to each side? Are they oceanic? Are they continental? Are they whatever? It's definitely a subduction. And then what kind of boundary is that? If you have subduction, and the volcanic arc on the western edge of the South American continent has what name? It's the Blank Mountains. And you may have heard of them. easily Googled if you didn't get it out of your readings or lecture notes, which I know that I talk about this mountain range. And I'm sure that Marshak did too in the book. Okay, so let me stop share and go back in. And okay, way over here on the right side of the map. Okay, there's South America, most definitely a continent. And here is the Nazca Plate. Here's the mid-ocean ridge, Pacific to the northwest, Nazca over on this side. There's a little tiny Cocos Plate here going underneath Central America. Okay, there's a trench. And then the name, well, it has it right here. And you may have already known that. Okay. Dark blue star. This star is positioned over part of the East Pacific Rise, which is a mid-ocean ridge. It's just that it's not very tall, so that's why they call it a rise. Compare this MOR to that in the Atlantic Ocean. Which ridge appears to have higher topography, meaning it sticks up further from the bottom of the ocean floor? Well, okay, here's the rise. And then we go up to the Atlantic. And there's the mid-ocean ridge in the Atlantic. Especially like right in here. Looks really tall, doesn't it? In fact, there are some places along this mid-ocean ridge that the ridge has gotten tall enough that it's actually an island. Whereas when we are down here looking at the Pacific, there's nothing that tall. I mean, these guys are taller. But along the ridge itself, there's really nothing there. So which one's taller? The Atlantic, most definitely. And part of that is because the spreading rate is slower. The Atlantic, for the Atlantic to open, it has to push the continents to each side to one side. And that's tough to do. Whereas the Pacific, that plate is a thin oceanic plate. There's no because continents are big, they're deep. Continents have roots, they're deep down and they push down into the mantle of the rock of the earth. And in order for them to move, the mantle has to move to the sides so that the deep parts of the continent can move there. But the Pacific plate is just a thin oceanic lithospheric plate. There's no down part to it, right? So it slides along pretty easily. In the Nazca too, so it gets pushed away from that ridge relatively easily, and then down the subduction zones it goes. And so that's the difference in the topography between the Pacific and the Atlantic at the mid-ocean ridges. Okay, so back to our question sheet. Why is there different topography in the mid-ocean ridges? What did I just say? And I'm sure the readings, certainly Marshak probably talked about this as well. Okay. And then the last question is about the Arctic Ocean. Use a supplemental map of the Arctic Ocean earthquake activity to answer this question. Which ridge, that marked with the yellow star or that marked with the red star, is obviously the active mid-ocean ridge underneath the Arctic Ocean? Not all that active compared to the other oceans, but it is there. Okay, so let's go out and take a look at not only the national geomap. Here's the Arctic Ocean. So here's Siberia over here on the upper left side, Alaska in the lower left, Greenland, and they're showing Greenland as being covered in water because they've taken the ice off of it. The ice is really heavy, and so it's depressed the actual rock of Greenland downwards. The bottom part of that continent has pushed its way into that kind of somewhat soft mantle. And so if you were to just melt all the ice off of Greenland right away, you would have a significant amount of the continent that's actually below sea level. That's why they're showing it as having water on top of it here. Okay, so which of these is the active? I mean, this looks somewhat like a mid-ocean ridge too, doesn't it? Well, here is the Iceland. We know that this is the mid-ocean ridge. And see how it propagates up like this? That's one clue. But let's take a look at the earthquake. Now, you have earthquakes along mid-ocean ridges, not only because of the divergence, but also because of the transform faults that are there, right? So if we look at the earthquake activity, that's in the other boundary maps supplemental. Now, here's Greenland over here. And there's Iceland, Canada, and then Siberia, Russia, and so on this side. So look, there's all kinds of volcanic or earthquake activity along the mid-ocean ridge here, and then going on along this one. That other one is over here somewhere, and there's like no activity there at all, right? So I think that this is the yellow one. This is where all the activity is, and there's no activity coming off of this part. Like it's right to the west of the north of Greenland. Okay, so here's right west to the north of Greenland. Look, there's just a couple of earthquakes out there, hardly anything. This was I forget what the time period was. That they were using here as to how long of a period of time, but even so, yeah, most definitely the yellow starred. Most definitely the yellow starred ridge, right? Go back and take a look at that map again. This one. That actually has the connection to the other part of the mid-ocean ridge in the North Atlantic. That makes sense, doesn't it? Okay, well, I've taken you through all of those questions, and hopefully it makes sense to you, and you can put all your right answers in. Again, it's going to be building, so you only the wrong answers, only the ones you get wrong the first time will show up when you go back in to put hopefully in the correct answer the second time around. Okay. All right. Hope I can get this recording up before the night's over here on Saturday night, April 9th.